All right, everybody have a good weekend. A little bit longer, maybe. Hopefully you had a holiday, at least part of it. All right, last time we were looking at the longitudinal pitching moment formula, the linear model, and we detailed the different values so we could calculate CM0, CM alpha, CMIH, and CM delta E. And the next thing we want to talk about is the aerodynamic center, which is the CG location where, you guys know this, where we have neutral stability. So just like for an airfoil, when you studied airfoils back in 324, if you take the pitching moment about the quarter chord point of an airfoil, the pitching moment does not change with angle of attack. So essentially CM alpha, the slope, if the pitching moment doesn't change, it's zero slope. And so that's the definition of an aerodynamic center of an airfoil. Same deal for an airplane. So this is the CG, so the center of gravity location. Yeah. I can't hear you. What?
The camera is not focused.
Yeah, I can't really do anything about that. It seems like the more I write, the better focused it is. Tell me, if I put an X down here, does it help? Yeah, isn't that bizarre? I think it's because this is glass and it's seeing reflections, and so I guess I always need to put an X down there. Okay, CG location where CM alpha is 0. And some of the webcams that I looked at, there's software you can download and you can fix the focus, but I haven't found it for this webcam. Yeah. So hopefully the more I write, the better it focuses in, and then you can get caught up. Better now? Yeah. So that means at this CG location, the CM alpha plot is just constant. So let's write the formula for CM alpha. And this is the collection of terms that we derived last time. I have to eat into this here. All right, so that's the formula that we derived last time for CM alpha. So is that second set of terms, it's everything that multiplies alpha. All right, so here's the CG. Here's the CG. So we're going to say, let's change those two values until we get 0 for CM alpha. So the formula then is going to be notice that I replaced the CG with this special location that's the aerodynamic center. All right, so then we solve for this. And after a bunch of algebra, you get this formula in the book for the aerodynamic center. And so this is nice because if you know your lift curve slope, the horizontal tail, if you know the lift curve slope of the wing, if you know the aerodynamic center of the wing, you know the areas, and you have an estimate of your downwash, and you know where your tail is located, you can calculate this. And of course, that's the CG position that we want to avoid because we want CM alpha to be negative for pitch stability. So this tells us how far aft the CG can be and maintain at least neutral stability. Of course, we want to be in front of that with the CG. And then you can show, and this is a homework problem. This is in homework number 3. Is that if you already know where the aerodynamic center is, it's really easy to calculate CM alpha for any CG position. And the way you're going to show this in the homework is you're going to take this here and you're going to substitute it up here. And you'd go, well, that's just going to leave a giant mess. But in fact, a whole bunch of stuff cancels out and you get that. All right, and by the way, this homework has now been assigned. This is due sometime in September. I forgot to pick up the sheet of paper that I printed out. It's due Tuesday. It's due Tuesday. Next Tuesday, your flight assignment's due. It's due the following Tuesday. 22nd? Okay. And while we're talking about dates, on your syllabus, it says exam 1 is on the 15th, and since we're doing the flight assignment due there, this is going to be on September 17th, which is Thursday. So next week, Thursday. And the key feature here is notice what it says on the syllabus as to what it covers. It covers chapter 1 and the longitudinal forces and moments, which is up to today. So that today is the cutoff for exam 1. And normally I do two exams in the class and then a final. And what I've done is I've chopped those exams up into 4 shorter exams seems like it'll work better. We can get those 4 exams in before everybody leaves for Thanksgiving, and then we'll just do an online final for the class. All right, so get those dates on your calendar. And this is an in-person exam, and we have tons of room in here to spread out for that. Okay, so we've developed the pitching moment values. We've talked about the aerodynamic center, which is a very important CG position to know. The last thing we need to add is the thrust forces and moments, because we've been developing lift and drag and pitching moment. Now we need the thrust, pitching moment, lift, and drag components. So is it defocusing? Maybe not yet because I'm standing up here. Okay, so thrust. Longitudinal forces and moments. So here's our airplane. And we're going to exaggerate this. Let's see, this is the x-axis going through like this. And then here is the stability x-axis, so that's pointing into the relative wind like that. And then we'll say there's a thrust line, and this is exaggerated, obviously. If you had your engine pointed that way, it'd be really weird. But this is the thrust line. And this is the angle of attack. And this is the angle that the thrust is relative to the axis through the airplane. And then the distance to that thrust line is called dt. So that's the perpendicular distance to the thrust line. And obviously we need that distance because that's going to be our pitching moment, the thrust times that moment arm. And then we're going to take components of the thrust. Remember, we want the forces in the stability axis. So we want, here's our subscripting deal here, thrust, force, in the x direction, steady state, stability axis system. You guys all get that? Force due to thrust, x direction, steady state, stability axis. Why is it what? That's just how that moment arm is defined. So you'd need to know how the engine is installed on the airplane, which direction the thrust points. All right, so this thing is going to be the component of the thrust in the x direction, stability axis. So it's going to be cosine, this should be alpha 1 because it's steady state, plus that extra angle due to the thrust. So that's this component of the vector there. Then the vertical component is the other one. So that's F T Z 1S. And it's going to be thrust sine And should I put a plus or a minus there? Should I put a plus or a minus here? Which way is positive x? Everybody point. X. That way. Which way is positive z? So what should I put here? Plus is correct, right? How about here? Yeah, we need a minus there, because this is z. And now the pitching moment is real easy. We already talked through that. mt1s is t times dt. And what should we put here, plus or minus? Based on how we define dt as positive thrust line above the center of gravity. It's going to be that way, going around that, right? Is that positive or negative? It's negative, right? All right, so that's the end of the longitudinal steady state forces and moments. Any questions about that stuff? So you guys are all experts on this, right? You will be after you finish the homework. Oh, you guys finished the homework. Everybody got it uploaded for me? All right, so next is lateral directional forces and moments, aerodynamic. And for these, there's less formulas and more pictures and concepts. So the key thing to focus on is physical understanding of the forces and moments. And for the vertical tail, we can actually calculate stuff. So if it's vertical tail, we calculate. If it's the other effects, we talk about it. All right, before we get into this, I want to define the angle of side slip again. I know we've done this, but it doesn't hurt to review it. So here we're talking about lateral. So let's draw the components. This is the, I'm drawing the axis like this now. This is a body fixed X, Y, and Z. I don't know why I turned it around, but I did. So the airplane's pointing to the right now. So X, so think of the airplane sitting here. There's forward, there's the right wing, and Z's down. And so the forward velocity is along the x-axis. The vertical velocity is along the y-axis, or the z-axis, and then the side velocity is like that. And those three added tip to tail form the velocity vector. And if we put the p on there, because remember p is the center of gravity, it's that point. So it's the velocity of the point. And go ahead and draw a line down here too, connecting that so it looks good. And then we can label this. This is angle of attack. Just by definition, that's the relative wind is coming in like this at that angle of attack. And then the angle outwards sideways to the wind is the side slip angle. And so remember, tangent of alpha 1 is going to be W1 over U1. So if you know both these components, you can calculate the angle of attack, or if you know the angle of attack on one of the components, you can calculate the other one. Then you can get the side slip angle like that. All right, so now let's say this is for just any general body fixed axis. Let's say we're now in the stability axis. The x-axis is actually downward pointed into the wind, so there is no W. All we have is U1 and V1S. So W1S is 0, and then we have U1S and V1S. So imagine tilting this axis so that we become stability and it's pointed along the dotted line. So we have U1 and V1, and that's it. So we still calculate the side slip and stability axis. Same way, because it's just the angle out there still exists. But because there's no W1, you can pretty much just say that U1 is the same as the total velocity for small side slips. But then how do we calculate alpha? Because if we tried to use this tangent of alpha 1s, W is 0. That doesn't make any sense. And when we tilt the axis down like that, essentially we don't know the angle alpha. But we do know W. So now alpha becomes an unknown that replaces W, which we now know. So we're not adding or losing any information. Up here, if we knew W, U, and V, we could calculate both. But now we know W, so alpha becomes an unknown that replaces W as an unknown. Remember, we're talking about like the 6 equations of motion in terms of U, V, W, P, Q, and R. Well, now we know W, but that equation for W that's known is now going to be used to calculate alpha instead. All right, so that's just some preliminary stuff. Don't dwell on that too much. As you go through the equations, it becomes obvious that this is what you get. All right, so now we need to do the rolling moment, yawing moment, side force. So number 1, rolling moment, steady state. So just like everything else, we do it in terms of coefficients because that takes out the dependency on sizes and the air velocity, and we can just focus on rolling moment coefficient. And then here's our linear model. And these are those variables that we had in that table that we said, okay, here's what we're going to say our lateral directional variables depend upon. And it makes sense. If you have side slip, you're going to get some roll. And let's get out the foam airplane. Yeah, that's the ailerons. So this is beta, crappy delta, rudder. All right, so longitudinal, is the camera focusing okay on this? Look okay? Decent. So longitudinal wise, we talk about angle of attack is going to affect lift, drag, and pitching moment, right? And then horizontal tail, wing, elevator obviously is going to affect things, and that's what we added in. So now you look at this and we say, okay, wind coming in from the side is going to push on the vertical tail and cause it to roll and yaw. So we want to include beta. And then the rudder being deflected is going to roll and yaw the airplane, so we add that in. And then the ailerons are going to obviously roll the airplane, so we add that in. So those are the major players in this model. And in fact, this model will look just like the yawing moment and side force. It's the same variables for all of those. Just like in longitudinal, we had angle of attack, elevator, IH, right? All right, so same deal is we look at which pieces of the airplane contribute to each of these. And we're going to start with CL beta. Typically, unless the airplane is not symmetrical, this is usually 0 because we have symmetry about the XZ plane, which we found out simplified the equations anyway. So usually that's 0. So how about CL beta? This is the rolling moment due to side slip. So I have to think about, well, which parts of the airplane, I need a little L there, sorry. Otherwise it looks like lift. Which parts of the airplane are going to do this? Well, the air coming in from the side can roll the airplane because it can hit the wing. It can hit the vertical tail. It can hit the horizontal tail. So those are the effects we're going to include. So it's the component buildup method. We calculate each effect individually and then add them together and assume that they don't affect each other. There is an assumption there. Depending upon the configuration of the airplane, you could have the wing closely coupled to the horizontal tail and they would affect each other. All right, so first part, CL beta of the wing fuselage. So like I said, there's less formulas here, but there's actually more stuff to remember, so it's a trade-off. The pieces that contribute to this are the wing dihedral, the wing position, on the fuselage, and wing sweep. And so I'll illustrate these with the foam airplane, and then the book has some really nice drawings, so I'll just pull those up. All right, so dihedral is the wings having an angle like this. And this is the main reason why you would do this, is because once I get this held right, if you have a component of the air coming in from this side, you can see how it's going to hit this wing and generate more lift on the right wing and less lift on the left wing, and the airplane's going to roll like that. More lift over here because of the air hitting it, If you have no angle, no dihedral, then you're not going to get that effect. Okay, how about the second one? Let's ditch one of our wings. If the wing is up on top, a high wing, the air comes and it curves over the fuselage, and again, it's going to push up on this wing and down on this wing. So you get the same effect. And then what else? Oh, wing sweep. We need the wings for that. We just ditched the horizontal tail, but that's okay. Okay, if the wing is swept, like that, can you see that okay? Wind coming in from the side is going to flow nicely over the airfoil here and produce more lift on this side. But on the other side, wind coming in is going to flow pretty much along the wing and produce less lift. So that is the foam airplane explanation of those three effects. And then the book has some nice pictures that I'm going to pull up. All right, so here's the first effect. Gamma is the dihedral angle. So this shows the angle of the wing up like that. And beta is coming in from this side. So the relative wind is going to push up on this wing and down on this wing. You get more lift. You're going to get a plus angle of attack increase here and a reduction in the angle of attack here, and that's going to roll the airplane to the left. So if you want to, you can add a plus lift here and a minus lift here. And again, that's because of the wind coming in from the side. Okay, questions on that? So if on an exam I say explain the wing dihedral effect on CL beta, this is what you draw. Yeah, it's left wing down, right wing up. So it's a negative roll. So let's add that to our picture here. So here, the wing dihedral due to beta, so CL subscript beta is negative. Roll right wing up. Now we haven't decided if that's good, bad, or we don't care. We'll get to that in a minute. All right, this shows the high wing effect. So if this is, the wing is up here, this is the high wing. It wasn't too bad, it was a straight line with this mouse. So the wind is coming in like this. You can see the wind curves up and over the fuselage. Obviously there's a velocity component up. You get an increase in angle of attack on the right wing. The flow comes around and back down, so you get a decrease on the left wing. And again, you get more lift on the right side, less lift on the left side. Try to say that fast. And you get the same thing. You get CL beta for a high wing. How about the wing sweep? Here's what I was trying to illustrate on the foam airplane. If you have a large side slip to the right, the perpendicular component of the velocity here going over the airfoil is pretty much most of the velocity. Whereas over here, a lot of the flow is going along the wing and you don't get the lift because it's not flowing over the airfoil as directly. So you get more lift here, less lift on this side, and you get the same rolling moment. By the way, why are we saying this is negative? I don't know what the Z is doing here. This is the x-axis. Right, thumb out the front of the airplane, right wing down is positive roll, so this is negative roll that we're getting. So now we have to ask ourselves, is this good? Bad? Don't care? Or for Clint Eastwood fans, it's ugly. You guys get that reference? You ever seen the movie The Good, the Bad, and the Ugly? This is an old movie. All right, so is this good, bad, or we don't care? It just happens. How many people vote good? How many people vote bad? So by default, you're choosing don't care. So maybe that's it. You don't care, you want to go home, right? Because you're looking forward to the cold weather tonight and the rain. Well, let's see if we can figure it out. It's not ugly, by the way. So here's our airplane. One way that side slip can happen, I guess I ought to be in front of the camera. One way that side slip can happen, oh, I'm still sharing the screen. Stop it. All right. So one way side slip can happen is the airplane, a gust causes it to bank like this. And then the airplane's going to start to fall, right? That gives us a side slip. What do we want to do to restore it back to level flight? We want it to roll negative, right? So that's the best way to remember it, I think, is it's a disturbance that gives you side slip. You want it to roll back upright. So often it's called bank angle stability. So the answer here is this is good. Now, too much of this can cause problems with the dynamic stability of the airplane that we'll study later on. So if you have a lot of dihedral and you have a high wing and you have a lot of wing sweep, you might get too much CL beta. And for some fighter aircraft that have a lot of wing sweep and get this effect, and you want them to be really responsive, they'll actually put anhedral into the airplane to cancel out some of the high stability so that the airplane was not so responsive to side slip. All right, so that's CL beta. And that's just the wing part. How about the horizontal tail? It's pretty much going to have the same effect, right? Only a lot smaller because the horizontal tail is smaller. So that's all we're going to write is ditto for the horizontal tail, but smaller. All right, well, that was easy. So now the vertical tail. And here we can actually get a calculation formula. So I'm going to go through this in detail. And we're going to discover that all of the derivations of all of the vertical tail effects are going to look pretty much the same. You say, I'm going to get this much lift sideways out of the vertical tail. It's due to this thing. And then we multiply by the moment arm and we get what we want. So first thing, draw a picture of the airplane side view. Let's make a really big vertical tail just to exaggerate here. Center of gravity is P there. X, XS, so draw this. There's the aerodynamic center of the vertical tail, so that's where the force acts. And we need the distance ZVS up to that because that's our moment arm. And the side slip is going to generate a force. And that's going to be clearer on the picture that I'm going to draw down here. So now this is a side view of the airplane. And so you're going to see the vertical tail there. So that's like you're looking down on the top of it. Gosh, did I say side view? Top view. This is side view. Turned upside down. That's a crappy airfoil. Let's make it look better. So there's the aerodynamic center. So that's that point there. Side slip is coming in like this. And so we're going to get a lift of the vertical tail generated like that. And the angle of attack that generates that lift is beta. So that's what we need to do. That's all we need to calculate the rolling moment due to side slip is because on the picture or on our foam airplane, we're saying we have side velocity coming in like this. It's going to hit the tail and produce a force right there. And that's going to push the airplane into a roll. Right? So that's force times the moment arm. It's an aerodynamic force. So we build it up from aerodynamic lift curve slopes. So the rolling moment due to the vertical tail deltas, because this is just its little effect, because we got the wing and the horizontal tail and all that other stuff. So we have CL alpha, the vertical tail, times its angle of attack. And then we have to turn it into a force. So we multiply by dynamic pressure S. So this is CL of the vertical tail, Q bar S. That gives us the force. And then we have to multiply, so I'm going to squeeze it in here, multiply it by that moment arm. It's the vertical moment arm up to the point where the force is acting. And is that positive or negative? There's foam airplane. Positive side slip, force this way. CG, AC of the vertical tail is above the CG. It's going to cause it to roll this way. Is that positive or negative? Negative, right? We decided that long time ago. And so to turn this into a coefficient, we divide by Q bar S, the stuff for the entire airplane. I need more room. Let's erase and move over. Let's go over here. All right, so CL is going to be I forgot my C, my B anyway. So the coefficient is Q bar SB divided by that. So let's fix that up. In fact, let's erase this so we don't get confused. So we divided by Q bar SB to get a coefficient. I lost a V on this. This is SV. Sorry about that. Should be what? No, this is just the rolling moment coefficient. And now we're going to take the derivative of it with respect to beta to get the change with respect to beta. Or if we want to do it like we did with the lift and the drag pitching moment, I'll do it that way. So the last thing we need to do is talk about our side wash model. And sigma turns out to be totally related to beta. So you can calculate it as the change in side wash with respect to beta. When beta is 0, you get 0 side wash. So if we plug this in up here, factored out of beta, and so all the stuff that multiplies beta is what we call CL beta V. Just like CL alpha was all the stuff that multiplied alpha in the CL expression. The other way to get this is to take the derivative of this with respect to beta, because that's all it is if it's linearly dependent upon that variable and you take the derivative of it, you get the slope. All right, so that took some work and some thought, right? But fundamentally, how do we do this? It's the force, aerodynamic, built up with a lift curve slope and an angle of attack times a moment arm. And then the rest is just algebra. You turn the rolling moment into a coefficient, spread stuff out, and then we factor out the variable that we're looking for, and we get the coefficient that multiplies that variable in the equation. All right, let's take a 3-minute break. Do I have what? Yeah. Should have said something a long time ago. You've been sitting there. How's it looking?
It's looking okay now.
But then
like,
when I stand in front of it, yeah. I need a cameraman and then a guy with cue cards. All right, welcome back. All right, so we've done this one. We said this is usually small, unless the airplane is really weird. We just did this one. And it's pretty complicated, right? The wing, dihedral, location, sweep, horizontal tail, dihedral, location, sweep, vertical tail, lift times the vertical moment arm due to the side slip. So how about the ailerons? So CL delta A is roll control. the reason that the ailerons are on the airplane is to give us this. So in this book, positive delta A produces a positive rolling moment. And your book has a nice picture of the ailerons deflected to do that. So the wing on the right, ailerons deflected up, we get less lift. Wing on the left, ailerons deflected down, we get more lift. And both of those combined together give a positive rolling moment. So if on an exam or a homework I ask you to draw a picture and describe from fundamental forces and moments the rolling moment due to aileron deflection, this is what you draw. That was easy, right? We just really have to define what's positive. Beyond that, it gets complicated. You have to know the lift distribution on the wing, and the size of the ailerons, a lot more details than we can do in just the general stuff we're doing here. All right, there is something called roll spoilers. That's what this figure is showing, is it's a flap on top of the wing. If you want to roll to the right, positive spoiler still gives positive roll. You deflect this flap up high enough so that the lift stalls, the airflow stalls going over the right wing, and you get stall here. And so the lift drops on this side, and you get that same positive rolling moment. We'll talk more about the difference between ailerons and spoilers when we talk about yawing moment due to aileron deflection. But for now, spoilers are another roll control device that we can use. And you can differentially deflect the horizontal tail if you have an all-moving tail. So for some fighter aircraft, you actually have all three things going on at once. You have ailerons, spoilers, and at low speeds, the horizontal tail will do this as well. And even on commercial aircraft, if you sit and you look out over the wing, when the plane is going slow, coming in for a landing, and it banks, you'll see the ailerons deflect all the time, and then the spoilers, when the pilot commands a higher roll rate, the spoilers will deflect as well to give additional rolling moment. All right, so there's actually 3 different devices on some airplanes that can provide a rolling moment. And so there's actually multiple or redundant flight control which is a good thing, because if the primary roll control device, the ailerons, breaks, you have backups. Something happens to the ailerons, you got the spoilers. Something happens to the ailerons and the spoilers, you've got the horizontal tail. Or we can deflect the rudder, and we'll talk about that. You can deflect the rudder and achieve roll from the rudder as well. An extreme case of this was flight number United Airlines Flight 118 on July 19th, 1989. And this airplane was a DC-10, which is also called these days an MD-11. And it has an engine here and an engine over here on this wing, and then this engine up on top under the vertical tail. And what happened was, and this flight took off from Denver, headed towards Chicago. And the compressor had an uncontained compressor blade failure on this engine number 2. Yeah, I think it's engine number 2, the one on top. And it blew through the side of the engine and took out the hydraulic lines that drove all the flight controls. So they lost all hydraulic power, and they lost elevator, rudder, and aileron. And so they declared an emergency. They were over Iowa, and the air traffic control said, hey, you're kind of almost headed for the Sioux City, Iowa airport. Why don't you try to land there? And they pulled a pilot who was flying in first class just to get some of his commuting somewhere else, pulled him into the cockpit, and he applied differential thrust on the engines in order to control the airplane. And he applied, in other words, to bank the airplane, he would apply more thrust over here and less over here, and it would start to yaw the airplane, which would create a side slip, which then pushed on the vertical tail, and via CL beta would roll the airplane one way or the other. It's not real good, it's not real efficient, but it allowed them to achieve bank angle control with the CL beta, the inherent stability. And then he would control the magnitude of both engines. If he lowered the throttle, then the airplane would pitch down and descend. And if he increased the throttle, it would pitch up and rise. And they were able to line up with the runway and crash land the airplane, saving more than half the passengers on board. And so this instituted or started a big research effort in NASA called Integrated Resilient Adaptive Control, where they tried to automate this. If pieces of the airplane broke, could a computer system adapt through artificial intelligence to help the pilot fly the airplane in the event of a failure? So there was a lot of work done with that. In fact, they demonstrated in simulators that this could be done, and that an adaptive flight control system could fly an airplane with propulsion-only control, which was what this was. So even all of the control systems gone, there's still additional redundant systems on the airplane that allow some control of the airplane. It's always a good thing. Yeah, there's the details. I pretty much told you the whole story. Engine number 2 suffered an uncontained failure, and it was over Sioux City, Iowa. The other wrinkle to this that Dr. Miller has talked about for a while is that the emergency crews at the hospitals and the EMS had just done a drill in the previous week about what to do if an airplane crashed in Sioux City, Iowa. And both emergency room staff were changing shifts, so at that point, both shifts were on call at the hospitals, so they had everybody available to rush out to the airport and grab the people and take them to the emergency room and save their lives. So it was a success story out of obviously a really bad situation. Let's see, what are we going to talk about next? We're almost done here. Oh, roll due to rudder. That's the last deal that we have. So we'll start with the foam airplane. If the rudder is on the trailing edge of the vertical tail and the vertical tail sticks up above the CG, if you deflect the rudder, it's going to yaw the airplane, but it's also going to roll the airplane because the vertical tail sticks up. So the rudder can also provide a rolling moment. And we can calculate that just like we did the rolling moment due to the vertical tail. So you'll see the derivation here is going to look the same. The only thing that changes is what's causing the lift. We're okay on time, aren't we? What does your computer say? I guess, sorry, I couldn't hear. 5 minutes left? Oh, 5:17. Yeah, we have time to do this. Gosh, these masks are horrible, aren't they? When a vaccine comes out, everybody get it, assuming that you're able to do that. All right, so we're talking about CL delta R. So if we look at our top view of the airplane, positive rudder is defined as trailing edge left, which produces a force in that direction because of the change in camber. And so the rolling moment is going to be that force generated by the rudder times the ZVS, the vertical moment arm. So that's why I said once you've done one of these vertical tail things, so this is the lift due to the rudder. We call it lift even though it's sideways. This is the rudder effectiveness. It's like that tau sub E that we had for the elevator. So it converts rudder degrees to angle of attack degrees, so we can multiply by CL alpha. This is the lift curve slope of the vertical tail. Oh, we have to multiply by Q bar S to get the total lift, sorry. So that's our force. And then we multiply it by ZVS. And that gives us the rolling moment due to rudder. And which way did we say it did? It rolled. Looks like from the diagram, positive rudder is going to produce a force to the right. It's above, so it's going to roll right wing down, which is positive. And so what's left to do is to turn it into a coefficient. And we're done. And so the stuff that multiplies rudder is everything except for the rudder. So that becomes CL delta R. All right, so that's it for today. We're done. Have a good evening. Stay warm. Can't believe I'm saying that. In fact, if you go to Colorado, not that you're going there, it's snowing in Colorado, I think. All right, have a good evening.